Okay, so now having melted the glass to some extent efficiently, because we are regenerating the heat, and we have now homogeneously brought the glass together in the neck, and we have reduced the temperature in the working end to 1100 degrees centigrade, and this is a very critical temperature, 1100. This is the temperature at which we can form the glass. The forming operation, like in most of the industries, to work on the glass and form the glass to the shape that we want. In this case of the glass manufacturing, we are talking about the dimensions and the thickness, okay, the width and the thickness. So, that is formed in the float bath. The initial introduction I talked about the float bath having molten tin. Why molten tin? When Pilkington brothers invented this particular process in 1957, till then the glass was being made vertically taken up, and the glass was trying to follow the gravity and sag, even though you have good set of rollers on the sides which were taking the glass vertically up, the Foucault and Colburn process since 1913. The optical properties were not as good because the glass was tending to sag and becoming wavy. And so Pilkington brothers thought, what is the best way to make the glass flat? So all of us know the flattest of flat surface that we can aim on earth is nothing but a liquid surface. So they thought, how about having two immiscible liquids like oil on top of water? If the glass can float on top of something which is molten condition, then we could make the thickness and the width when the glass is floating, then that could give a very, very flat surface. This idea is what propelled to what we now know as the float glass manufacturing process. So they found that it is possible, and for which we need very importantly three properties for the medium, or rather the substrate on top of which the molten glass can float. One, the glass is at a density of 2.51 kg per liter, and so necessarily the substrate needs to be at a higher density, much higher density than the glass itself, so that whatever happens, the glass will always remain on top of the substrate rather than the other way. Okay. Tin, as I already said, tin is the medium that we use. At 7.3 density is very, very high in comparison to the glass, so that glass will always float on top of the tin. So it fulfills the property number one in terms of density, the glass to stay on top of the substrate floating. The second, the good temperature in which the glass can be formed, as I said, is 1100 degrees centigrade. So at this temperature, the glass has to remain a liquid. And when we can take the glass out of this bath, it can be taken at around 610 degrees centigrade. This is the temperature in which we can say that the glass is now rigid enough to travel on rollers. So at the temperature of 610, also the tin or the substrate needs to be in liquid form. So even at 1100 or 600, we need the substrate to be in liquid form. So the melting point needs to be much, much lower, and the vaporization temperature need to be much, much higher than 1100. So the vaporization temperature of tin at 2300 is much higher than our highest operating temperature 1100, and the melting point of tin at 231 degrees centigrade is much, much lower than the lowest operating temperature of 610 that we maintain at the end of the float bath. So the tin, in addition to three other metals which fulfill, is chosen because of its availability and the price, and so the tin, about 200 to 250 tons of tin, depending upon the size of the float, is poured into the float bath before it is started off, and then the glass, when it arrives into the float bath on a continuous basis, it comes at a very steady pull rate, as we call the tons per day, the way it is accounted for. It comes and pours, the flow of which is controlled like how we control the water flow in a dam through a sluice gate. The same way, at the end of the furnace there is a tuile which is regulated to open more or less to keep a control of the exact quantity of the glass that is designed to flow into the bath. The glass flows into the bath at 1100 degrees centigrade, and then it pours in, and then we need to do some work. Let's a little bit digress and talk a little bit in general. Let's take cooking oil, and I pour a small quantity, let's say 5 ml in one place, a 50 ml in another place. It spreads. It spreads differently, but because this oil is the same, it has got the same viscosity, it spreads and forms a thickness on its own, and the thickness remains same. Similarly, when we pour the glass onto this molten tin, it forms an equilibrium thickness of 5.7 millimeter at 1100 degrees centigrade with the viscosity of the glass. If 5.7 is the only size we need, we don't have to do any work, just pour and take it out and we give it to the customers. But we need to make anywhere between 1.4 millimeter, 1.6, 1.8, 2 millimeter, 2.5, 3, 4, 5, 6, 8, 10, 12, 15 and 19 millimeter glass which is produced on this float bath. So, for different thicknesses we need to make the glass thinner, then we need to make the glass stretched and make it thinner. The equilibrium thickness, to repeat again, is 5.7 millimeter. So, if you want to make a glass thinner than 5.7, we need to stretch the glass and make it thinner. If you want to make a glass which is thicker than the equilibrium thickness of 5.7, we need to compress the glass and make it thicker. And this is done on the bottom right picture. As you can see, there are 3 pairs of what we call as the top roll that is shown in the picture. Some of the float lines could use as high as 10 top rolls depending upon the thickness that we use. This top roll machine has got a cylindrical head which goes inside the bath and gets nibbed into the top of the glass on both edges. This top roll machine can have 4 operating properties. One, it is rotating, and when it is rotating at an anti-clockwise direction in such a way that it is pushing the glass forward. The speed at which it can push the glass forward, we have a control. So, this top roll machine has got a control of speed. Second, I can push the glass forward, at the same time I can make the glass, I can make the top roll a little bit open up or close, which means in addition to moving the glass forward, I can also open the angle of the top roll machines such that it is stretching the glass outwards. If I close the angle to a negative angle, then I push the head of the top roll inner side towards the top roll, thereby I am making the glass thicker. So, second property or the parameter we can operate the top roll is the angle. In addition to that, we need to take the top roll in and out, and also depending upon the width we need to operate at a certain penetration. So, there is a possibility to make the top roll go in or come out, and then how much nip you need to give, how much strength you need to give for the glass from the top roll machines. So, we need to have a nipping mechanism. So, the top up and down is operated as well with the top roll. So, using this 4 set of properties or the parameters of the top rolls, we provide the thickness of the glass. Now, let us understand a little bit more. I talked about the angle, how the speed helps in determining the thickness. Let us assume, for example, the first top roll machine, the speed at which it is pushing the glass, I can set it at, let us say, 2 meters per minute. So, whatever is the glass is coming at a constant flow rate, and it is moving 2 meters in 1 minute duration. The next top roll, I increase the speed to 3 meters per minute. Same quantity of glass which has been traveling at a speed of 2 meters per minute. Now, the second machine is forcing it to travel faster at a speed of 3 meters per minute. So, it covers a larger area and naturally the thickness reduces. And then third top roll, for example, I further increase the speed to 5 meters per minute. So, what has come in 2 and then meters is become 3 meters, now it is 5 meters. So, it is going to reduce in thickness much more. So, when I have to make thicknesses which is too small, for example 2 or 1.8 or 1.6 millimeter, we need to employ more number of top rolls to keep on incrementally increasing the speed and stretching the glass more, and as well given a big incremental difference between the one top roll to the next top roll, so that we get the thickness to the lower side. On the other side, if I have to make the glass thicker, I have to compress the glass and make it thicker. The first top roll, the same quantity of glass is coming. I keep the top roll speed at 10 meters per minute, and then the glass is traveling at 10 meters. Then second top roll, I reduce the speed to, let's say, about 8 meters per minute. So the glass has been traveling fast, suddenly you put a brake and allow it to go slowly at 8 meters. This is the thickness build up that you can see. The next top roll, I reduce it to 6 meters per minute, further the thickness builds up, and progressively if I want to make extreme thicknesses like 15 millimeter or 19 millimeter, then we keep on employing more number of top roll machines and have a big difference between the speed from the one top roll to the next top roll, by way of which we could provide the different thicknesses that we want. So just to summarize, the float bath is the place where the float glass manufacturing, the name comes from. Glass is floating on a molten tin bath. The flattest of flat surface that anyone can aim on the earth is a liquid surface. So glass floating on a molten tin provides a very flat medium when we form the glass, and since the glass is formed when we have the flattest of the substrate, the glass that we produce in this method provides the best optical quality that so far the manufacturing processes have given us. And how the thicknesses is given, we spoke about the top roll machines which predominantly decide how the thicknesses are formed. Out of the 4 parameters, the penetration, the nipping, the angle and the speed and the angle contribute significantly to the thicknesses that we want to manufacture. And when we have to make a glass thinner than the equilibrium thickness, that is from 2 to 5 millimeter for example, we need to increase the speed and open the angles. And if you have to make the glass thicker, we need to decrementally reduce the speed, starting with a high value in the first top roll all the way down to a lower value on the speed, and close the top roll angles, which will give us the thicker glass. So this is the float bath process. And further, once the thicknesses are given, the glass is allowed to cool down. There are a few aerial coolers which are put in the downstream of the top rolls in order to help the glass reduce its temperature to about 610 degrees centigrade. At this temperature, the glass is taken on the rollers. When the glass exits the float bath, now it passes into the annealing layer. The annealing layer, as you can see, there are various segments that are given, and in each of the segments, the method in which we cool is different. In some of the segments, for example, in the A zone, the way the air is provided is a cold air. It's in a co-current form. We can cool the glass very fast. The B segment is divided into B1, B2, B3, a very long range. We have a reason for that. I am going to explain that in a few seconds. And after that, it's a C zone, in which again a cold air, mass quantity of air is being passed to have a little bit of faster rate of cooling. And in the D zone, it's a preheated air, but direct cooling with passing of the air in contact with the glass, not through the ducts as it's done in A, B and C zones. And in F zones, it's done with mass air, cold air directly into the glass to cool at a faster rate. Now let's little bit talk about what is this annealing range of the glass. The glass that we make, as you saw in the raw materials, is using silica, soda, as well as the calcium, magnesium, etc. So the type of glass that we make comes under the category called as the soda lime silica glass. The soda lime silica glass, the annealing range is the temperature range of 480 to 540 degrees centigrade, which means above the temperature of 540 degrees centigrade, the glass is said to be plastic in state, which means whatever you try to do to the glass, nudge it, poke it, whatever, it doesn't take any stress because the glass is plastic, it gets back to its original shape. Below a temperature of 480, the glass is said to be elastic in its state, which means you cannot induce any stress onto the glass permanently, but you can break it. But this temperature range of 480 to 540 for a soda lime silica glass. This is the annealing range in which whatever stress happens remains permanently in the glass. And this 540 to 480 temperature is actually cooled in the B zones. That is why you have a very, very longish B zone divided into, in some cases it could even go bigger furnaces these days with 1000 ton capacity, for example, have B1, B2, B3 and B4. So we have a very, very slow rate of cooling in the B zones. Why we need to have slow rate of cooling? For example, the rate of cooling, if it is uniform, you will not have any stress, the stress will remain neutral. But the glass is traveling on a roller, you can cool the top, you can cool the bottom. Only after the top and the bottom is cooled, the center gets cooled. At any point of time, the temperature on the surface on the top, bottom and the center will always remain different. And the rate of cooling will also be very different. For the simple reason, we will have stress on the glass. All that what we can do is to reduce the stress closer to neutral. Okay. To give you a simple example, what gives us the best stress profile? For example, let us take an example of a balloon. You blow a balloon and you prick it with the pin. It does not form a hole, it blasts open. Why? Because when the balloon is blown, the forces are acting away from the body, tensile stress. So the moment you initiate a puncture into the balloon, the tensile stress takes this hole and makes it into a rupture. Let us take another example of a car tire. A nail finds it difficult to penetrate into the car tire, but if it penetrates, unlike a balloon, it does not burst because the rubber of the car tire is made with compressive stress. The forces are acting towards the body. So similarly, when we are having high tensile stress, when you try to cut the glass, it has a small impact, the glass can shatter and break like how a balloon is blasting. When you make a high compressive stress onto the glass, you may find it very difficult to cut, like in a car tire, the nail might find it difficult to penetrate inside. Similarly, we might find it difficult to cut the glass. That is why when you do a toughening process, we need to pre-cut the glass and then you toughen the glass, because you cannot cut the toughened glasses. Like an eraser, for example, which has got a mild compressive stress, you will be able to slice it with a very clean edge. So what we are aiming at in the annealing process is to have a good cutting quality, and the glass has to come out without any breakage. It's better to have a mild compressive stresses on the edges. And this is done with a very slow rate of cooling using various blowers and different control mechanisms which are inbuilt into the annealing layer. And now the glass is cooled to a temperature of 60 degrees centigrade. Now it's time to meet the customer's requirement in terms of meeting the dimensions as well as the other quality. For the glass to remain longer in a humid conditions, even to avoid the problem of weathering attack, the glass is sprayed with zinc citrate on line. So all the glasses that you buy will have zinc citrate coating, protection against weathering, which can happen because of a humid atmosphere, and the glass is stored in the warehouse for a longer time. So this is a process that you see on the picture. And the next is, we talked about the stress profile on the annealing layer, and there are online equipments which measure and tell us continuously how much is the stress on the glass, so that we can regulate and avoid bad stress glass being sent to the customer. Online we also have, all the float lines are equipped with high-tech detection devices which can spot defects, unmelted raw materials, or bubbles which come because of a poor refining, which we talked about, the CO2 that has to escape out of the glass. If not done efficiently, it can pass into the glass. Even the defects that we can't see by naked eye, even with good lighting, there are scanners which can tell us where these defects are, and these are scrapped online. That's a detection system. Having detected and scrapped all the bad glasses, and now the good glass alone travels into the cutting line, The cutting line, depending upon the customer's requirement, has different possibilities to cut, and as you can see, you can cut it into a big size glass called as a jumbo glass, or you can cut it into medium sized glasses which is called as a DLF, or the small standard size is called as a SSS. You take it into the stackers and robots. And just to tell you, when we think of a glass manufacturing typically in a conventional way, we always think that it is a very, very high temperature, people are working very toiling and very dusty atmosphere, but the technology has facilitated these days that all the hot end and the cold end cutting controls as well as the furnace operations, float bath operations are done through distributed control systems. There is very minimal people interactions they need to do are minimized. The exposure to the heat and dust is absolutely not there, and even when you come down into the cutting line to pick the sheets of the glasses, it's quite like any high technology industry that you would see. There are a lot of robots and stackers which pick up the glass without any need for humans to do this activity. So this is the float glass manufacturing process, and I hope you got some information related to what you are looking for. Thanks for watching.